Hello, these are the solutions to activity 7. So we're asked to rank these compounds in order of increasing lattice energy. So I'm looking at these compounds here. The first thing I want to take notice of is the charge difference. So I got a +1 minus for KCl. So this should be plus minus. I have a +2 -2 for the next two compounds for calcium sulfide, magnesium oxide. I'm just looking for the row of these atoms in the periodic table. Calcium's common ions a +2, sulfide -2, magnesium +2, oxide -2. I got a +2 -1 for magnesium fluoride, and the same thing for the chloride. And so the idea here that I'm using is that my energy of electrostatic attraction is equal to kappa Q1 Q2 divided by D. So when I have a plus and a minus, and I have the electrostatic attractive force that has to be overcome to break the attractive force between these ions. So the lattice energy for any of these compounds would be the reaction like this, the reaction of the solid ionic compound going into gaseous ions. So energy has to be overcome in order to, if you will, vaporize this compound. So the delta H here has to be endothermic, has to be greater than 0, because energy has to be overcome to break the attractive force between the plus and minus ions. It's just a question of how much. If we increase the magnitudes of charge, so think about the magnitude of Q1, the magnitude of Q2. If we increase those charges like we did for magnesium oxide and calcium sulfide compared to KCl, their lattice energies are going to be a lot higher. So +2 -2 lattice energies, these are going to be the highest lattice energies. This is going to be the lowest. So I'm going to have KCl as the lowest. And then I'm going to have the +2 -1s in the middle. And then the +2 -2s last. And then size comes into play here. So if the ions are closer together, if their distance relative to each other is closer, if the ions are smaller, then we get those ions closer together, and then a greater amount of energy has to be applied to break that attractive force. So the energy of electrostatic force of attraction, if we put the ions closer together, then they're that much more attracted together. So being closer, being smaller is better in terms of requiring a lot of energy to break that electrostatic force of attraction. So the greatest energy here is going to be for the smaller magnesium oxide. That's going to have the greatest lattice energy. Calcium sulfide next. So I'm just comparing the +2 -2s and looking at their size differences. Being smaller means more energy has to be overcome to break the +2 -2 of MgO than CaS. And the same thing would hold true for the +2 -1s. Now their magnitude's higher than the +1- because we have the higher magnitude of charge for one of the ions. But then being smaller allows the force of attraction to be greater. So higher lattice energy for MgF2, which is higher than calcium chloride. And you'll generally see the lattice energy trends coincide with melting point trends. So the melting point tends to coincide with the lattice energy, kind of showing you that there's some importance of the strength of this ionic bond. The stronger the ionic bond, the higher the melting point, the higher the lattice energy. Question 2. We're told here iodine's more electronegative than hydrogen. When we're thinking of electronegativities, hydrogen's relatively low. Our left side elements are NO, F, Cl are relatively high in electronegativity. Sulfur, bromine, iodine, relatively electronegative, but not as high as, say, the sort of most electronegative elements, NO, F, Cl. So we're just told this here so that we know that iodine's more electronegative. So if I have a bond like this, where my Lewis structure for HI, which should have 1 + 7 for 8 valence electrons. So I have 8 valence electrons here. My formal charges would work out to be 0 for both these atoms. But then I have to think about the relative pull the nuclei have on the bonding pair of electrons. So the formal charges assume the electrons in the bond are equally shared, 0 formal charges. But then the actual charges aren't going to be 0. We're going to pick up some partial negative charge on the iodine, a partial positive on hydrogen. This is due to the electronegativity of iodine being greater than hydrogen. So iodine has a stronger pull on the bonding pair electrons than hydrogen does. So we're going to pick up some negative charge on the iodine atom. Now how much, we can calculate it for diatomic molecules using the dipole moment and the bond length and a couple of conversion factors. And so we can calculate the charge Q. So our dipole moment mu is equal to Q times R R is the bond length, the distance that the charge is being separated. So I can calculate Q by taking mu over R. And so then I just have to account for units here. So I take 0.44 debye as my dipole moment. I'm going to convert this into SI units, coulomb time meters. So 3.34 times 10 to the minus 30, excuse me, I did this conversion backwards. 1 debye is equal to 3.34 times 10 to the minus 30 units coulombs times meters. Then I'm going to divide this by the bond length that I convert over to meters. So my bond length would be 1.61 angstrom, and 1 angstrom is a 10 to the minus 10 meter. So it's 1.61 times 10 to the minus 10 meters. And so that allows meters to cancel, debye cancel, so I get the charge in units of coulomb. And then I just convert and use the electron charge here. That 1.602 times 10 to the minus 19 coulombs is a charge of 1 electron. So in electron charge units, the charge relative to that of an electron, I can calculate that here. I take 0.44 times 3.34 e minus 30, divide by 1.61 e to the minus 10. If we hit enter, that's the number of coulombs. It's really small. It's times 10 to the minus 21. We divide that by the charge of an electron. And I get that the charge is 0.057 units of electron charge. And remember the units of electron charge, if it were H plus I minus, we'd get plus 1 electron. We'd get 1 electron here, so it'd be plus 1 electron minus 1 electron. So we're saying this is a partial charge. The charge is less than that of 1 electron. And so the partial negative on iodine is going to be negative 0.057 electron charge units, and the charge on hydrogen will be plus 0.057 electron charge units. So we're calculating the partial charges on H and I in units of electronic charge, just using the charge of 1 electron as that final conversion factor. So let's give a couple Lewis structures for diatomic molecules. For diatomic molecules, what I would do is just take into account the number of valence electrons, like for O2 is 12. I have to satisfy, if I can, the octet rule. So the only way I can satisfy the octet rule for oxygen is with a double bond. And so a double bond gives each O 8 electrons each. So the octet, when we count the bonding pair electrons along with the lone pair electrons on a given atom. So that's how I get 8 electrons around each oxygen atom. And then if I want to calculate the formal charge is where I would break the bond in half. If I break the bond in half, that's where I calculate the formal charge. Each O should have 6 valence electrons, and they do. So each oxygen is neutral in charge. So nitrogen, 2 times 5. Just have to look at the periodic table or know that nitrogen has 5 valence electrons each, so I only have 10 valence electrons. You could go dot structure. There's nothing necessarily wrong with trying to start with a dot structure and then just kind of pairing up the lone pairs to make a triple bond. So, and we could also just say, well, nitrogen to get to an octet for each has to have a triple bond, because this gives each nitrogen 8 electrons in its valence. And then, so it allows them to satisfy the octet rule while also, in this case, maintaining 0 formal charges. So each nitrogen should have 5 electrons of neutral charge, and they do. So just for the formal charge, just break the bonding pair electrons exactly in half, and it's the charge that those atoms would bear if the bonding pair electrons are equally shared. Same type of structure for CO. We have 10 electrons as well, so we have carbon triple bond to oxygen, just like in N2. Only difference here is that oxygen should have 6 electrons, it only has 5. So here oxygen has a charge of +1, and then carbon's charge ends up being negative. There's nothing we can do about it. This is just the best Lewis structure we can come up with. Carbon should have 4 electrons, only it actually has 5. So that's how carbon has a -1 formal charge. So despite oxygen being more electronegative and wanting electrons more than carbon, carbon ends up being the atom that bears a negative charge. Now the bonding pair electrons will shade towards O. The next problem, we're going to try to quantify actually what these partial charges are in CO and see that the bonding pair electrons are still going to slant themselves towards oxygen, but carbon's still going to end up with the negative charge. Oh, maybe it's not the next question. The question 5, I think, comes back to carbon monoxide. But question 4, before we get there, choosing the more polar bond, we're looking for separation or difference of electronegativity. So we're trying to figure out which atoms are more different in electronegativity. If I have these atoms here, the electronegativity is increasing towards fluorine. It also then increases towards fluorine in both directions. So the difference between carbon and chlorine is going to be smaller than that of carbon and fluorine. So fluorine's electronegativity is higher than chlorine's. So fluorine's higher than chlorine. So the difference between carbon versus fluorine has to be greater. So we get a bigger difference of electronegativity for CF. Also, if you think of, iodine versus the other halogens, that if you take IBr versus ICl, the difference of electronegativity between ICl is greater because you have a greater difference of electronegativity. So more polar for ICl. So we're looking for differences in electronegativity to determine bond polarity primarily. Now, dipole moment is equal to Q times R. Sometimes we get a little bit confusing and we might say which one has a bigger dipole moment, but I think a better question is ask which one's more polar. More polar is kind of getting at Q. The magnitudes of charge are going to be highest whenever you have that greatest difference of electronegativity. The actual dipole moment itself, a little complicated. It has a dependence on the bond length, and the difference of electronegativity. But think of the charge magnitude. When we talk about polarity, it's really getting at which atoms have the greatest polarized bonds or the greatest partial positive and negative charges building up on their atoms. So NH or NO. So hydrogen's electronegativity is relatively low. Nitrogen is relatively high, but it's not as high as O. So hydrogen's low, oxygen's higher, so we get a bigger difference between the OH bond than the NH bond. So the OH bond would be more polar than the NH bond. So you're just trying to get a sense of, the atom H is low in electronegativity, and then you're looking for the atom that has then the highest electronegativity, that would be O. So we get the greatest difference of electronegativity. And so whatever answer that ends up being, it's like answer C. Okay, back to question 5, kind of getting at carbon monoxide. So despite carbon being less electronegative than oxygen, the carbon atom in CO bears a negative charge. We saw that in the Lewis structure. We can see that too. The dipole moment of CO points towards carbon, meaning carbon's the atom that bears that negative charge, but the dipole moment relatively small, not very big, 0.122 debye, and the bond length 1.13 angstrom. Can we calculate the partial charge on the C and the O in this compound? So again, we're kind of, the dipole moment here is still pointing towards the carbon because that's where our negative charge is. It's just going to be a partial negative and a partial positive. We saw that the formal charge was -1 and +1. So we're going to see how the electronegativity of O plays a role in adjusting the actual charges from these predicted formal charges from assuming that bond pair electrons are equally shared. Okay, so we can calculate our charge just like we kind of did before, taking the dipole moment, divide by R, and then account for units. This problem here, I really wanted this to be more an example of this, how we can kind of look at the charges. It gives us another chance to do this conversion, but to me, it's just such an interesting problem that we can do this and kind of compare the magnitudes of charge. So I take the dipole moment, convert it to Coulomb meters, just the SI units, and then I take the bond length, 1.13 angstrom, which is 1.13 times 10 to the minus 10 meters. That's an easy conversion. I just do that to cancel into Coulomb meters. And then I convert the number of coulombs that an electron, the charge of an electron. So the charge of one electron is 1.602 times 10 to the minus 19 coulombs. That cancels out the coulomb. So that gives us the charge relative to that electron. And let's calculate and see what it is for carbon and oxygen and CO, 0.122 times 3.34 E minus 30, divide by 1.13 E to the minus 10, and then divide by 1.602 E to the minus 19. And I get that Q is equal to 0.0225 units of charge relative to that of an electron. And the charge here is a charge that's being separated. So we have the plus Q on the more positive atom. So the partial positive on O is plus 0.0255 electrons, and then the charge on carbon is minus 0.0255 electrons. So we have the minus Q on the one atom and then the plus Q on the other atom. And then we just need to use the Lewis structure, our predicted formal charges, and then the thought electronegativity to help us figure out which atom bears the negative charge. Carbon bearing the negative charge here, oxygen bearing the positive charge. This is what gives carbon monoxide its unique set of properties, and really unique set of unfortunate properties, in that it's so toxic to breathe in, because the carbon binds the hemoglobin in a way that CO2s that usually bind through the oxygen atom, that CO2s bind reversibly to hemoglobin, and then you can exchange CO2 for oxygen, but carbon monoxide does not exchange to myoglobin and hemoglobin in a way that allows it to ever come back off. So you can be poisoned with carbon monoxide. Okay, let's calculate some formal charges here. So calculate the formal charge of all the atoms in these two Lewis structures. So I see one for, and this would look like for PO4 3 minus the Lewis structure for phosphate ion. And so let's start with the left structure here. So I have, if I break this pair of electrons in half in this bond here, I would have an oxygen that looks like this. And I'm really just trying to assess what's the charge of that O atom. What would its charge be? Well, its charge would be negative 1, because we have oxygen that's picked up an electron relative to the count it should have for a neutral charge. So I could say that this charge here should have 6, has 7, so it's minus 1. So these oxygens all have a minus 1 formal charge. And then this one here would be equal to 0, because it should have 6 and it does have 6. So I have a 0. And then my phosphorus atom, phosphorus should have 5 valence electrons, and it has 5 electrons closest to it. 1, 2, 3, 4, and 5. So that would give it a neutral charge. And so minus, 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 and then 0 and 0. So if I sum up all these formal charges, I should get the charge on the ion, and I do. And so I have 3 minus O's, 1 0 O, and a phosphorus at 0. And then my other Lewis structure here that I can calculate the formal charges in, I can take phosphorus here, should have 5 electrons surrounding it, only has 4, so that's plus 1. So I have a positive 1 formal charge on phosphorus, and then all the oxygens are negative. They look just like the negative O's in the other structure. They're all 6 minus 7s, and so minus, 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 minus. So I have 4 minuses and a plus. That sums up to minus 3. So all the formal charges should sum up the overall charge on the molecular ion, and it does in this case. And so, so these are the formal charges for phosphorus and O in these two Lewis structures for phosphate ion. So we're asked which Lewis structure violates the octet rule. If I call one Lewis structure A, the other Lewis structure B, Lewis structure A would violate the octet rule because it expands its octet of phosphorus. Expanding octets mean count all the bonding pair electrons. I count 10. 8 should be the max according to the octet rule. And so this would be an octet rule violation. Doesn't necessarily make the Lewis structure wrong just because it violates the octet rule, unless we're talking about second row atoms. So once you're in the third row, phosphorus is in the third row, atoms can expand their octet in some Lewis structures. And it's acceptable to sketch those types of Lewis structures, or it's not necessarily wrong because of the expanded octet. If I had a structure for like a nitrogen atom, where I had something like this is wrong because second row atoms cannot expand their octet past 8 electrons. So second row atoms cannot expand octets. Third row, you'll see some expanded octets. Which one minimizes formal charges? So we minimize the formal charge of one of the O's and the phosphorus atom in Lewis structure A. Okay. So Lewis structure A, despite violating the octet rule, minimizes the formal charges. And so sometimes we call Lewis structure B the Lewis structure that satisfies the octet rule or doesn't expand the octet rule, and then Lewis structure A is the one that will expand the octet but to minimize magnitudes of formal charge. Now, sometimes we try to describe which one of these Lewis structures is more correct. You'll see both sketched in science. You take OChem, you'll see structure A probably more predominantly than a structure like B. I think B is probably more accurately a description of what phosphate really looks like. I don't really think you can truly expand octets. I don't know how we would describe the bonding in a double bond here, but you know, you'll see these two types of Lewis structures. But I think the best one, and usually the one that we'll ask about, kind of is more about this structure here. But a lot of times you'll see a question if there are two acceptable Lewis structures. I would say these two Lewis structures are acceptable. The one I circled is probably better. But a lot of times we'll ask, give us a Lewis structure that satisfies the octet rule, or give us a Lewis structure that minimizes formal charges or satisfies the so-called formal charge rule. Question 7, let's sketch some Lewis structures here. So for BCl3, now there's kind of like two basic approaches. One basic approach would be to take boron with 3 valence electrons, take chlorines with 7, just from their count on the periodic table, and you'll come up with the Lewis structures pretty straightforwardly for a lot of molecules. We'll struggle with most ions, so I usually won't use this approach if I have an ion, but if I try this with like the phosphorus F3 compound, same thing. Fluorines have 7 valence electrons, so I can pair those up. So this isn't necessarily a bad starting point, but like I said, if we have an ion, if we have maybe one where we have more than 3 or 4, if I go beyond 4, I don't know. Like there could be a point where we decide we want to have a more formal rule. The more formal rule would be count the number of valence electrons, 5 for phosphorus, 3 times 7 for the fluorines. That's 26 total electrons, and then just start with your central atoms, single bond the non-central atoms to the central atom, complete the octets of the non-central atoms. Don't necessarily complete the octet of the central atom with electron pairs. So if I'm doing BCl3 this way here, we'd have 3 plus 21 for 24 electrons. And so I have no electrons left over to put a pair of electrons on boron. So this is the best Lewis structure for BCl3. And then for PCl3, I have 2 electrons that are unassigned, so I have to put those electrons onto the central atom, so I would add those electrons here after the fact for PF3. So leftover electrons, when we're counting them up, go onto the central atom. And then if I do SiCl4 this way, silicon has 4, 4 times 7 for the chlorines, so that's 32 electrons. So that's going to be a central silicon, 4 fluorine single bonded, chlorine single bonded. Complete the octets of the chlorines. And that's all 32 electrons, so no electrons left over for the central atom in SiCl4. And so that's good. We might calculate formal charges at some point. All these formal charges are 0 in BCl3 and PF3. Also, silicon has 4 valence electrons. It has a 0 formal charge as well. And so if I ever see a case where I don't have 0 formal charges, I might consider making multiple bonds to minimize magnitudes of formal charge. I might think about, again, like the previous example, do I want to expand the octet or not? Generally speaking, the question will guide you in terms of if you should expand the octet or not, if you should minimize formal charges. And so we'll see a few more examples as we continue, but let's look at HCN. So if I'm doing it, there's a few different ways I can think of doing this, but the easiest way, I think, is just adding up all the electrons. I get 10 electrons, and then single bonding to the central atom, completing the octet of the non-central atom. If I do that first here, that uses all 10 electrons. I have none left over for carbon, but then I have a 2 plus formal charge on carbon, and I have a 2 minus formal charge on nitrogen. Nitrogen should have 5, but it has 7. So why don't I rebalance the charge? I also haven't satisfied the octet rule of carbon. So what if I make a double bond over here? That reduces the formal charge to plus and to minus. So plus 1 and minus 1. That's good. So use multiple bonding to reduce magnitudes of formal charge and also help you satisfy the octet rule. So if I make another double bond, get rid of the electron pairs here, I then have a triple bond. So I have H to carbon, triple bond to nitrogen, and then nitrogen has 8 electrons surrounding it. Carbon has 8 electrons surrounding it. Hydrogen likes 2, so we got 2 there. So we're all satisfying their respective noble gas count of electrons, and then also using the proper count of electrons. If you're ever shown a Lewis structure, just double check the count of electrons. Does it make sense for the molecular ion that's shown? So last one being ClO4 minus. Now this one here, I'm probably going to the rules and not doing like a dot structure. Whenever I have like an ion, it's almost always going to be easier to add up the 7 plus 4 times 6. I have to add 1 for the minus charge. That's kind of one of the keys here. I have to add 1 electron to get a negative charge overall. And so that gives me a total of 32 electrons. So I'm going to have essential chlorine, 4 oxygens. I'm going to satisfy the octet on the O's. And then I can calculate formal charges. I have minus all the way around on the oxygens. Should have 6, I have 7. That's minus. And chlorine should have 7. We only have 4. Just think of breaking those bonds in half. So chlorine only has 4 electrons closest to it. That's plus 3. And so I have a plus 3 formal charge. Now I can do one of two things. I can either accept this as one of the possible Lewis structures because I'm satisfying the octet on chlorine. And then the only way to decrease the magnitudes of formal charge would be to make double bonds that expand the octet of chlorine, which, again, you will see these Lewis structures like in the book and in some other sources as a Lewis structure. I don't like anyone I wouldn't like saying that this is the only acceptable Lewis structure because I think probably, this Lewis structure here is probably better. But we can reduce the magnitudes of formal charge. So we're now down to 0 and 0 for these Cl and Os, and then minus for the other oxygen. And so all the formal charges, again, summing up to the overall charge on the molecular ion. Number 8, how many equivalent yet different Lewis structures can be sketched for carbonate ion? So that would be 4 plus 3 times 6 plus 2 for the negative charge. That gives me a total of 24 electrons. So in a lot of ways, this kind of starts like BF3, but just where I have carbon and oxygen instead. So I have carbon, oxygen, complete oxygens, octets. Now the difference between carbonate and BF3, at BF3, I got to this point, I had a 0 formal charge, but I now have a positive formal charge on this carbon. Why is that? Should have 4 valence electrons, I only have 3. So I have a positive 1 formal charge, and I have all these negative oxygens. And so think of the positive charge pulling a negative electron in to make a double bond. So we can make that structure here that would have a 0 formal charge. Carbon now has a 0 formal charge. So I've reduced the magnitudes of formal charge. So I'd have a 0 formal charge O, 0 formal charge carbon, and 2 negative oxygens. But then I can sort of resonate, meaning move the electron pairs around the structure and sketch different Lewis structures that are equivalent yet different. What do we mean by this? What we mean is that this Lewis structure is identical to the one we first sketched. If we call this Lewis structure A, this is Lewis structure B, that Lewis structure B is identical, but it's different. It's different in which oxygen and carbon are making the double bond, and then we sketch this over to here a third time. So I can sketch 3 Lewis structures that are equivalent yet different. So how many Lewis structures can I sketch? The answer would be 3. And the issue is, or the idea here, kind of complicated, but the real molecule doesn't care about these Lewis structures that we just sketched. The real molecule isn't ever A versus B versus C. So it is not doing this. It is not interconverting. What the real molecule does, and there's a picture for this that we'll see, I'll show it to you in the notes, but there's a picture where we can get a simultaneous set of orbitals that all overlap simultaneous, so that that extra double bond will always be shared simultaneously at all times. That's the idea of resonance. That electron pair just spreads itself out across all 3 of these bonds simultaneous. So instead of having a double and 2 single bonds, we really have 3 bonds that are equivalent. So I have 3 bonds that are each sharing 4 pairs of electrons across those 3 bonds. Now, if you think of a single bond shares 1 pair of electrons across 1 bond. So like a hydrogen-hydrogen single bond, this is 1 pair of electrons across 1 bond. That's a single bond. If you think of an O2 double bond, that's 2 pairs of electrons shared across 1 bond. So that's a double bond. If you think of a triple bond, you have 3 pairs of electrons spread across one bond. Here what we're doing is we're spreading 1, 2, 3, 4 bonds across those 3 connections of C and O. So I have 3 CO bonds, and I'm spreading 4 pairs of electrons across them at each time. So each of those bonds is going to be, if you think of bond length, the double bonds are shorter, single bonds are longer. These are kind of like right in between the length you would expect for a single versus a double bond. This question here, rank the CO bonds in the following molecule by increasing bond length. And so the idea here is that single bonds are longer than double, which are longer than triple. So having more electron pairs will shorten a bond. And so carbon monoxide is the triple, carbon dioxide is the double, methanol has this type of Lewis structure here. Now, how do we get this Lewis structure? Well, one way would be that if you take this to be your central atom and you kind of attach all your electrons, let's even say, like let's leave these off for a minute and say, how do you get the Lewis structure? Well, one way could be just by picturing something like this, and then you're just pairing up the hydrogens, and you're just pairing these up, pairing those up, and so that's one way you get the Lewis structure for methanol. Another way could be, if you just think of counting the electrons, I have 4 for the hydrogens, plus 4 for carbon, plus 6 for the oxygen. That's a total of 14 electrons. And again, if we're not sure, and we're just sketching our Lewis structure and leaving these electrons off for a minute, we'd have the outer electrons kind of getting their octet satisfied. So 2, 4, 6, 8, 10, and then the only place left for electrons is O, or 12 and 14. So again, this is oxygen with a single bond, and then our carbonate is at 4/3 bond, right in between. And so if we think of single bond, the bond order here would be 1, the bond order would be 2, the bond order would be 3, 4/3 should be right in between. And so CO should be the shortest, followed by CO2, followed by the bond length of the carbon-oxygen bond in carbonate, and then followed by the bond in methanol. So methanol having the longest bond because it's the closest, it's the single bond. It's the one that only shares 2 electrons. We get a little bit more electron pairs in carbonate, even more in carbonate, even more in carbon monoxide. You can look these up. Carbon monoxide, we just did it on the one example. This is 1.13 angstrom. CO2 is around 1.2. You can double check these. Carbonate, I think, is a little bit longer, and then methanol the longest, probably like 1.4-ish. Final question for the activity. Determine the Lewis structures for a couple of different molecules here. So NO, what do we do for NO? We have 11 electrons, so there's an odd count. So one of these atoms has to violate the octet rule. And let's this would be NO minus. This would be where we have 12 electrons to distribute. So this would be NO minus. Remember, we did this in class. We'd have a 0 and a -1, and that's, we end up with a negative on the end, but we kind of had to because we have to satisfy the octet rule here. And so for NO, the question is, do I kick an electron off of the N or the O? So for NO, let's not use that symbol. So for NO, do we go with this structure here, where we kick the electron off the nitrogen, or do we go with this structure here, where we kick the electron off the oxygen? And so the difference here, they each have 11 electrons. It's just which atom do I kick the electron off of? Do I take it off the N or do I take it off the O? And well, let's look at formal charges. So 0 here, so break the bond in half. I get 0 for oxygen and then 0 for N. And then if I go with this structure here, I get negative for O, positive for oxygen. This is bad. There's no reason a Lewis structure would choose to put a formal charge of plus on the O and a negative on the N. We want the more negative if possible on the O. We want to reverse those charges, or ideally, let's minimize them. So let's minimize magnitudes of charge if we can, and we can do that with this structure here. So the formal charge rule just says minimize those magnitudes of formal charge if it is possible. What about N2O? We're told N's a central atom. Let's do our rule. Give an octet to the non-central atoms. Let's count our electrons. 16 electrons in total. And that's 16 distributed. So I have 16 electrons distributed, so no lone pairs for nitrogen. So now I have a big formal charge of 3 plus. And so what can I do? Well, I can pull electron pairs in to make a double bond. So let's pull this in here. And so that's good. That reduces the formal charge down to +2. This one was -2. Now it's just -1. This oxygen here is -1. Okay, now what do I do next? So now I can either make a double bond with the O. Like if this were like CO2, we do this. If we're like CO2, I do that. Now I don't do that for N2O because that would keep the negative charge on N, not on O. So why don't I make a triple bond here? So why don't I make this triple, leave the NO single, leaving that at minus, and then that makes this oxygen, or the nitrogen formal charge, the first one in the compound, be 0, and then this nitrogen here is positive. So this Lewis structure here turns out to be the best Lewis structure for N2O. Now you might be sitting there thinking, well, you just talked about minimizing magnitudes of formal charge. Why would this Lewis structure then be wrong? So why would it be wrong to consider this Lewis structure? So what's wrong with this one? What's wrong with this one is I don't have enough space around nitrogen to pack 10 electron pairs. So second row atoms cannot expand their octet. So we cannot minimize magnitudes of charge to expand the octets of second row atoms. I think it's possible that we're not even doing it for third row atoms, but at least third row atoms are bigger. You can maybe imagine the Lewis structures expanding their octets. So we're not expanding an octet for a second row atom. So we'd stay at the Lewis structure that puts the 0 on N, the negative on O. And let's do one more, SCN minus. So if we're counting 6 plus 4 plus 5 plus 1, so we have a total of 16 electrons again. So kind of the same basic type of structure we just had before. The connection would be linear here. That's why we would write it in this way. So SCN minus, S to C to N. Lone pairs around, and then we'd have negative formal charge, -2, +2 formal charge, so we're going to make a double bond. And so let's go with the -2 first. That takes it down to minus. Nitrogen's more electronegative, so let's kick this in here and to make sulfur go to 0. And so this one here ends up at sulfur, double bond to carbon, double bond to nitrogen, 0, minus, and 0. And if we try to make the triple bond to the nitrogen, then we'd be putting the negative charge on sulfur. We just have to remember NOF are the most electronegative. Sulfur's electronegativity is lower than NO and F. So NO and F, the highest electronegativities. Chlorine is also the next highest, sulfur lower than them. Okay, so that's all of the problems for this week's activity. So good luck and have fun.